So we're trying to play PhysicsMUD, and that's a game here where, I got my M3 laboratory deep space station that I'm chilling in, and we're gonna be visiting three different planets. So we got Electrodynia, Quantara, or Matharion, and these are the three planets we can visit, and they all got their own little regions. So today I want to go to Quantara and see if we can practice some quantum mechanics. So let's land on Pontara and let's look around and see what the areas are. I don't need a thing. I need text-based description because this is physics mud. We don't need any pictures. So here we are in hyperspace and we go into the classical navigation flickers. Now we're no longer at a point, but we're at a distribution. So we descend through the layers of clouds where we can't really see too much. Everything's oscillating. Trajectories split, recombine, and we got this quantum Hilbert frame. So here we are on the planet. Montara is not a terrain. Below exists a superposition of states. And since it's okay, so we have some places we can navigate to. We can go to the Schrodinger Basin Operator Hall, the bound state lattices, the spin matrix citadel. Holy crap! Um, let's go to an easy area for now. An easy area. I want to go to an easy area. So we're going to the wave packet expansions in the beginner region. Okay. Oh my gosh. We've met a monster already, so suddenly we have a drifting Gaussian packet is materializing in front of you. And it waits, but it's asking this particular question here. The free particle packet is initially localized. As time increases, what happens to the packet's spatial width and why? Spatial width expands radially outward, like the light cone. I don't know, we'll see. Not expanding like a light cone, but there's no causal front. Free particle wave packet spreads because it's a superposition of momentum. So, oh, the different momentums cause it to spread out all directions, the entire spectrum. So I guess this is it. Localized ones. The spread of momentum. Well, I'm gonna put that in my little notebook because that's kind of a nice thing to do. So we're gaining some skill here. We're going to the wave packet experience points are being gained here. Um, these things expand due to momentum distribution. Okay. Um, look. This is usually a command that you send when you're playing these text-based games. Look, what do I see? Hopefully I'm playing this game still. The ground beneath you is no longer solid. It appears as a soft lattice of probability density. Okay, we might want to cross this Gaussian ridge. And there's a Schrodinger basin. Cross Gaussian ridge. Let's see what's across the ridge. Step forward. The probability peak lowers and widens. Ridge does not collapse, but it spreads faster locally. Stability here is about phase alignment. No enemies yet. Let's observe the interference. So the amplitudes add, realize there's a cross term. That's a nice little equation. I want to add that to my little note. Wave packets. So how can I do this? Combination operators and stuff. Let's move this over here. And we'll go in there and we'll add this little equation we found. We found an item. This little pickup right here. Getting a little equation. Some free experience points. Plus, and so what is this? A cross term? Is this some kind of interference pattern? Plus 2, the last cross term here. Interference. Okay, so let's go ahead and see what's happening here. Yes, we gained some insight indeed. Let's carefully cross the interference. I'm treading carefully because I don't really know too much quantum stuff. It's like really hard. So we're placing our boots on constructive bands to avoid the null line. Alright, halfway through the interference pattern. Oh my god, we have a fringe warden appearing. Jesus Christ. Multiple choice. Easy. Okay, it's gonna be an easy one. One task. As you cross the two-wave interference region, what action would most directly erase the interference fringes? Oh my god, increasing the particle's mass m. Measure which path information, determine which packet the particle came from. Normalize the total wave function or wait longer so the fringe is sideways. I'm gonna guess it's B because these two don't really make a lot of sense. Measuring which path information, determine which packet the particle came from. We'll see. We'll see if that's the correct answer. Correct. Whew. Which path information destroys the relative phase decoherence? Which path information? What do you mean? Which, actually, I kind of want to ask this in a different. What do you mean the which path info removes interference? How? This is weird. Probabilities across term. Yeah. Okay. Let's bust out the paths. So we have two paths. Well, we have this equals side 1 plus side 2. two paths. If you obtain which path information, the particle becomes entangled with something else. Okay, that's really weird. Oh my god, this is some complicated stuff. So how does this work? Instead of instead of this, we have psi 1 plus psi 2 with a cross tensor and this d naught term. The state becomes two separated ones. Here we have no path info, and on this side we have path info. Eraser. One, here's two, which path info. Interesting. Now compute the probability without observing the detector. Doesn't really make a lot of sense, but okay. Okay, so what can we do now? What can we do? Let's go ahead and move to Schrodinger basin. Here the environment is dominated by static potential. The ground curves inwardly smoothly. Free spreading halts, sloshingly oscillate. Time evolution does not erase structure, it repeats it. Hmm. And the basin walls glow at faintly specific heights, the allowed energy eigenstates. Physical meaning. This is quantum stability. The bound state sentinel condenses the basin floor. Wow, so now we have a new encounter. Let's go ahead and open our free write. See what happens here. So this is conceptual. Why does a wave packet in a confining potential fail to spread indefinitely, unlike a free particle? Man, I don't know. Maybe because the potential creates a boundary condition. Confining potential, yeah, this is time evolution over here. Let's see if we can figure out where that might be. Sure, let's put it like here, I guess. Time evolution. So we can have 5 feet in here, xt, and then we have another wave packet, x, where we take e, negative e I n, P over H bar. So what's the great insight here? Spatial shapes do not change. Because all components remain spatially confined, the packet can spread indefinitely. Spatial confinement means so there's spatial confinement, but oscillation and momentum, I don't know. Probability does not spread to infinity. It's time dependent, and the momentum fluctuates. Well, the momentum fluctuates, or the phase fluctuates. Both, both, but in different senses. Phase always evolves. All right. So I guess we have spatial confinement means momentum fluctuates. Okay, so here we are, looking out at the basin. There's something. A localized packet near me breathes. The hum is periodic. For now, the basin holds. Um, let's move the harmonic oscillator wells. Moving deeper into the into Quantara. Here we go, we're going deeper. Harmonic oscillator wells. The region is mathematically perfect. Everything oscillates cleanly. We're supposed to be seeing some visual images as we go into rooms. Okay, well, anyway, here's the ladder sentinel. He's appearing from the evenly spaced energy bands, and it's asking, why do wave packets in a harmonic oscillator potential oscillate without spreading? Wave packets in a harmonic oscillator potential. I think because the potential creates a well that uh, energy sloshes up and down like a skateboard. Half pipe, but that's classical. So the energy gaps are identical. Let's take a look at that Earnfast equation. What is it again? Earnfast equation. No, Earnfast theorem. Let's put a new one here. The Ehrenfest theorem. D over dt squared position plus w squared x. And this is like a packet center moved with classical particle. The center acts like particle. And the oscillator interesting. The even spaced energy levels allow the phases to be synchronous. What's that quantum oscillator? Um, even spacing allows phase synchronization. Well, that was interesting. Just check something real quick. Right, I still have quite a bit of time. Move to bound state lattices. So now we're in a rigid, structured, discrete bound state lattice. We notice that standing waves exist within each well. Energy levels have split into bands. Periodicity. Eigenstates are no longer localized, they are block-like. Feel a subtle pull towards the left along the lattice directions. The block wardom assembles from repeating eigenmodes. Its form replicated at every lattice site. Whoa. So here's the counter. Here's the encounter. Why does a particle in a periodic array bound states form energy bands rather than isolated energy levels? Oh my god. This question is insane. Why does a particle in a periodic array of bound states form energy bands rather than isolated energy levels? Well, usually, particle in a box has energy levels. But if we put a lattice of these pieces together, then we would notice a band of overlapping uh, levels. So it creates a long band surface band energy. Yeah, this is like crystal bands or something. Well, that was interesting. Well, let's let's go back to the Pontara main uh, landing site and look around what areas there are. Let's go back to the landing site and let's see what kind of areas there are. Wow, so we're actually heading into the highest territories here. Go to central potential orbit zone. What the fuck? Move to central potential orbit. Alright, we're leaving the landing hub and we're going to the central potential orbit. Everything here is organized around a single center. So we're no longer moving across space, we're moving around it. Okay, probability density forms rings and shells stacked concentrically. I wonder if it would be better to put this on the right side. There we go. Nodes appear as spherical surfaces with angular seams. Nothing prefers right or left, only radius matters. Oh, wow. The central potential. Why can the Schrodinger equation be separated into radial angular parts? And what physical symmetry allows this? And, well, azimuthal symmetry removes the C component. So we're left with R and theta. That's 3D polar, where we go 0 to pi instead of 0 to 2 pi. Might have taken some damage here. Full rotational symmetry. Hmm. Okay, this is actually a really complicated idea here. Azimuthal symmetry means that we can rotate around one axis. Full rotational symmetry, so that's SO2. Okay. Let me see if we can try to like explain this somehow, because I don't even know where I wrote this kind of stuff. Rotational symmetry. I don't know what degeneracy in M means, but um, quantized. This is full rotational symmetry around all axes. So in SO2, the function is independent of phi, but in SO3, function still has both angles. That's interesting. So basically, if we have azimuthal symmetry, is SO2 around one axis? So let's say, move this a little bit down. Azimuthal symmetry is SO2 around one axis, meaning independent of phi. As this, C says, and here we have to basically say, yeah, we have this YLM angle, there, something like that. Okay, did we take some damage? Yeah, I'm on the quantum planet. I'm on the planet of Quantara, as we can see. We didn't take any damage during the Quantara, this last enemy that we just fought for whatever reason. But essentially, yeah, we just went and we fought a drifting Gaussian packet. Um, well, thanks for tuning in. Quantara. We fought the Fringe Warden. We fought the Bound State Sentinel, the Ladder Sentinel, the Block Warden, and I think there's one more area, right? One more area, the Hydrogen Spectral City. You might have to go to the Hydrogen Spectral City. So here we are, we're going to the perfectly symmetrical radial corridor, and the city is built from allowed transitions, have no continuous flow, only emission lines. This is what we see, we focus. And here is the Quantara encounter. The spectral archivist materializes. This is another conceptual question here. So why does hydrogen emit light only at discrete wavelengths? And what determines the allowed spectral lines? Um, yeah, so the atomic spectrum of hydrogen causes the wavelengths to be emitted from only, I think there's like 3 frequencies. But I don't know why these frequencies are specific. I can't remember why the frequencies are allowed. More than 3. And the reason they're allowed is very precise. Yes, we have these series, right? Why the wavelengths are discrete? Energy levels? Um, we should have taken some damage there. Quantized bound energy states. Anyway, so that was kind of cool. Um, there must be more monsters here on Quantara that require problem solving. It must be like a hidden area somewhere on Quantara. Well, yes. Yes, but where are these monsters? Let's go back to the landing site in Quantara. Look around. You must have missed an area. The operator crossing. Okay, fine. We're hanging out at the operator crossing here. Okay, let's do this last one here, and maybe we'll call it a day. The commutator shade. Okay, so we're evaluating x comma h. I'm pretty sure that's I. No, 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 no. That can't be. The 1D harmonic oscillator. I mean, I know what the. If we look at the notes over here, they'll like tell me. But I'm kind of forgot. Let's take a peek over here. We have that. That's not the same. Hmm. Maybe I don't have that written anywhere, which is fine. We can learn something new here. Uh, I'm gonna guess it's I H bar. No, it can't be. Maybe P squared over 2M is Vx. I have no idea. Like, this is crazy. Don't know what kind of. I guess we're taking damage here. Okay, x. This is velocity. Is 1 over a molar 8 x comma h divided by I h bar, which is somehow equal to P over M. I guess that's an momentum. Oh my god. Okay, so let me just write this down over here. I don't even know where I could put this, but I'll just shove it here in like the commutator region. And as this commutator gets time evolution, this is one of the most important commutators. Well, what's the status? Or my health status? Or my HP should be pretty low. It's really hard for this robot to keep track of my HP. Okay, yeah, so okay. This is really funny, but yeah, we're gonna save this game and hopefully we'll be able to come back later and see if we can continue because you know that was pretty cool. We played a little bit of physics mud and we were in Quantara, the quantum planet. So we had a little bit of fun. We learned a few things. Hopefully next time it'll be a little harder. I don't really know these solutions very well. Anyway, thank you all for watching.